It was built at tremendous cost of American blood and treasure. 38,000 workers died building the Panama Canal. They died of malaria, they died of snake bites and mosquitoes. Not a nice...
Every week, America secretly drops 15 million flesh-eating flies over Panama, and what happens next will blow your mind. These bloodthirsty insects literally eat animals alive from the inside out. Cattle die screaming, deer's skulls get exposed, humans become living hosts. The US government runs massive factories, breeding millions of these nightmare creatures. And here's the shocking part. Other countries are begging them to do it.
Because Canada and the United States, that would really be something. You get rid of that artificially drawn line, and you take a look at what that looks like, and it would also be much better for national security. Don't forget, we basically protect Canada.
Now, if you're thinking this sounds like some sort of biological warfare program, or perhaps a plot from a science fiction novel, you'd be forgiven for that assumption. After all, when you hear about government facilities specifically designed to breed millions of dangerous parasitic insects, only to then drop them from aircraft over foreign countries, it does sound rather sinister. But the reality is far more fascinating and, believe it or not, represents one of the greatest success stories in the history of pest control. The United States government has been running factories, actual industrial facilities, dedicated solely to breeding these flesh-eating flies. These aren't small operations either. We're talking about massive production lines that churn out millions of insects every single week, year after year, decade after decade. And the governments of other countries, particularly in Central America, aren't just tolerating this situation. They're actively cooperating with it. Panama, where one of these facilities operates today, has welcomed this program onto their soil. Mexico participated for years. Other nations in the region have been involved in various capacities. So what on earth is going on here? Why would anyone want to breed millions of dangerous parasitic flies? Why would you then load them onto planes and scatter them across thousands of square miles of tropical forest? And perhaps most puzzling of all, why would other countries not only accept this, but actually support it? The answer to these questions involves a remarkable story that spans more than 70 years. It's a tale of scientific innovation, agricultural desperation, and one of the most unusual weapons ever deployed in humanity's ongoing battle against nature's more troublesome creatures. This isn't about killing flies or spraying pesticides or any of the conventional methods you might expect. Instead, it's about using the flies themselves as the solution to the fly problem, turning the insects into unwitting agents of their own species' downfall. But before we can understand the solution, we need to understand just how serious the problem was. For thousands of years, these flies terrorized livestock across the Americas. They caused excruciating suffering to animals and occasionally to humans as well. They cost farmers and ranchers enormous sums of money. Entire herds could be affected. Young animals were particularly vulnerable. The economic impact ran into millions upon millions of dollars annually, and this was just in the United States alone. When you factor in Mexico, Central America, and the Caribbean, the scale of the problem becomes even more staggering. Farmers tried everything they could think of to protect their animals. They applied ointments and treatments to wounds. They kept animals indoors when possible. They inspected their herds constantly, looking for the telltale signs of infestation. But despite all these efforts, the flies always found a way. They were persistent, adaptable, and seemingly impossible to eliminate. Generation after generation of flies would hatch, mate, lay their eggs, and continue the cycle of destruction. For most of human history, people simply accepted these flies as an unavoidable fact of life, much like mosquitoes or ticks, or any of the other parasites that have plagued humanity and our domestic animals since we first began keeping livestock. If you raised cattle or sheep or pigs in the southern United States or anywhere in Latin America, you knew that screwworm flies were part of the deal. You factored the losses into your business model. You did what you could to minimize the damage, but you never imagined that these flies could actually be eradicated. That all changed in the middle of the 20th century, when a small group of scientists began thinking about the problem in a completely different way. Instead of trying to kill the flies directly or protect animals from them, these researchers asked a more fundamental question. What if you could make the flies unable to reproduce? What if you could somehow sterilize them, release them back into the wild, and let them mate with fertile females? producing no offspring. The female flies would waste their reproductive potential on sterile males, and over time, the population would collapse. It was a brilliant idea in theory, but turning theory into practice would require overcoming enormous challenges. How do you sterilize millions of flies? How do you breed them in sufficient numbers in the first place? How do you transport them to where they're needed? How do you distribute them effectively across vast areas of territory? And perhaps most crucially, how do you convince governments and farmers and ranchers that this unusual approach, which required breeding the very pest you were trying to eliminate, was actually worth attempting? The story of how scientists and government officials answered these questions and turned this wild idea into reality is what we're going to explore. It's a story that involves everything from World War II radiation research to problems with airline cargo regulations because the flies smelled so terrible. It's about factories that consume thousands of gallons of blood every week, planes that used to be military aircraft now repurposed for insect distribution, and an invisible barrier stretching across one of the narrowest points of the American continents that has held firm for 5 decades. This program has been running continuously since the 1950s. It has cost hundreds of millions of dollars over the decades, and yet economists and agricultural experts agree that it has been worth every penny, saving far more money than it has cost, and preventing immeasurable suffering for millions of animals. It stands as proof that sometimes the most effective solutions to our problems are the ones that seem the strangest at first glance. To understand how this entire operation works, we need to start at the source. Somewhere in Panama, about 20 miles east of the capital city, sits a facility that most people would struggle to categorize. Is it a farm? Is it a factory? Is it a laboratory? In many ways, it's all three, and the hybrid nature of this place reflects the unusual mission it serves. The facility occupies what was once a sugarcane plantation, repurposed now for a very different kind of cultivation. This isn't the first place where flies have been bred for this program, but it represents the current state of the art in mass insect production. And when we say mass production, we're not exaggerating. This facility produces approximately 20 million flies every single week. That's not a typo. 20 million living, breathing insects, all of them grown, processed, and prepared for release into the wild, week after week, year after year. But this operation in Panama is actually the successor to earlier attempts at industrial fly breeding. The very first facility of its kind was built back in the United States, in the city of Mission, Texas. That original plant was designed to produce up to 200 million flies per week at its peak capacity. Think about that number for a moment. 200 million flies. That's more than half the current population of the United States, except we're talking about insects, and we're talking about producing that many every 7 days. The people who designed these facilities quickly discovered that breeding flies at this scale presented challenges that nobody had really considered before. The primary issue was food. These particular flies, being members of the blowfly family, have very specific dietary requirements. Their larvae don't eat just anything, they eat flesh. Living flesh, specifically, which is what makes them such dangerous pests in the first place. So if you're going to breed millions upon millions of these insects, you need to feed them appropriately, and that means providing meat on a scale that quickly becomes both logistically complex and extremely expensive. The scientists working for the United States Department of Agriculture initially tried to replicate the fly's natural diet as closely as possible. They fed the larvae a mixture of warm ground beef and blood. Now, if you're thinking that sounds expensive, you'd be absolutely right. Beef costs money, and when you're feeding it to millions of fly larvae every single week, those costs add up remarkably quickly. The program administrators soon realized they needed to find more economical alternatives. Over the years, they experimented with various substitutes. They tried horse meat. They tried whale meat when it was available. Pork was tested. Cow lung, which is less expensive than standard beef cuts, became an option. At one point, they even used meat from nutria, which are large semi-aquatic rodents that look somewhat like oversized rats. Interestingly, Louisiana was dealing with a nutria problem at the time, as these aggressive rodents were taking over wetland areas, so using their meat for fly food solved 2 problems at once. Despite all these attempts to find cheaper alternatives, the amount of meat required remained staggering. By 1962, the facility in Mission, Texas, was consuming 108 tons of meat every single week. That's over 200,000 pounds of meat, week after week, and that wasn't even counting the blood. The facility needed 10,000 gallons of blood weekly to keep the larvae properly nourished. Just imagine the logistics involved in sourcing, transporting, storing, and processing those quantities of animal products. But feeding the flies was only one challenge. Once you've bred millions of insects, you then have to transport them to wherever they need to be released. And this created an entirely unexpected problem that nobody had anticipated. The flies smelled absolutely terrible. We're talking about an odor so offensive, so overwhelmingly foul, that commercial airlines simply refused to transport them. The cargo was too disgusting. Pilots and crew members complained. Other cargo would be affected by the smell. It seemed like an insurmountable problem, until someone came up with an ingenious, if somewhat absurd, solution. The workers began spraying the boxes of flies with cologne. Apparently, dousing containers of millions of flies with perfume made them just barely tolerable enough for airlines to accept the cargo. One can only imagine what the cargo holds of those planes must have smelled like, even with the cologne. The facility in Mission eventually shut down in 1981, when the fly breeding operation was moved first to Mexico and then ultimately to Panama, where it continues today. The modern facility represents a significant evolution in both technology and methodology. While the basic principle remains the same, breeding millions of flies for release, the actual process has been refined and improved over decades of experience. One of the most significant changes involves how the larvae are fed. The modern facility no longer uses raw meat, which is honestly a relief for everyone involved. Instead, the larvae receive a specially formulated diet that's considerably more economical and easier to handle. This diet consists of powdered blood, powdered milk, and powdered eggs, all of which are reconstituted with water and then thickened with cellulose to achieve the right consistency. Now, before you start thinking this sounds more appetizing than raw meat, you should know that when this mixture is poured onto the larvae, it looks like sewage. It's a gray, viscous substance that probably wouldn't win any awards for appearance. But the flies don't seem to mind. They're insects, after all, and their standards for food presentation are considerably lower than ours. The important thing is that this diet provides all the protein and nutrients the larvae need to develop properly, and it does so at a fraction of the cost of feeding them actual meat. The facility itself is designed like a carefully orchestrated production line, which in many ways is exactly what it is. 115 people work there around the clock, maintaining 24-hour operations 7 days a week. The building is a concrete structure without windows, which might seem unusual until you realize that controlling the internal environment is absolutely critical to the process. Inside, the facility is divided into different rooms, each one optimized for a specific stage of the fly's development. Temperature and humidity are carefully controlled in each space, creating the perfect conditions for each phase of the insect's life cycle. The larvae, for instance, hatch in a room that's heated to 102 degrees Fahrenheit. This temperature was chosen deliberately because it simulates the body temperature of an infected animal, which is the natural environment where these flies would normally develop. After hatching, the young larvae are moved to cooler rooms where they're fed and allowed to grow. The facility has even adapted industrial equipment for its unique purposes. There's a modified pill counting machine, the kind you might find in a pharmaceutical factory, that's been repurposed to dispense larvae. This machine spits out exactly 15 ounces of larvae at a time onto aluminium trays. These trays are then stacked in piles of roughly 50, creating these towers of developing insects. It's industrial efficiency applied to insect agriculture, and it works remarkably well. Just 2 days after the larvae are placed on their feeding trays, they've transformed into fully grown flies. At this point, they're moved to a cold room, where the temperature drop causes the insects to enter a dormant state. They're not dead, just sleeping. Their metabolism slowed by the cold. In this sluggish, dormant condition, the flies are much easier to handle and transport. The dormant flies are then placed into metal boxes, each one roughly the size of a washing machine. These boxes are loaded onto aircraft for the final stage of their journey. And this is where things get particularly interesting, because the distribution method for these flies is almost as remarkable as the breeding operation itself. The planes used for distributing the flies are small turboprop aircraft, the kind you might see at regional airports making short hops between cities. But these particular planes have been modified for a very specific purpose. Each one can carry approximately 2 million flies per flight, and they've been equipped with a constantly rotating dispersal mechanism installed in the belly of the aircraft. This machine works somewhat like a sprinkler system, except instead of water, it's distributing living insects across the landscape below. If you're thinking this sounds rather high-tech, you should know that the original method was considerably more primitive. In the early days of the program, a technician would literally sit in the plane and drop small cardboard boxes filled with flies out of the aircraft by hand. The boxes were designed to break open upon impact with the ground, releasing the flies. However, this method had significant problems. Sometimes the boxes wouldn't break, they'd hit the ground intact, and the flies trapped inside would simply die, wasting all the effort and resources that went into breeding them. The rotating dispersal system solved this problem, ensuring that the flies are released into the air rather than sealed in boxes on the ground. The planes fly relatively low, typically no more than 1,500 feet above the ground. This altitude is carefully chosen because it gives the flies the best chance of survival. At this height, they're close enough to the ground that they don't have far to fall, but high enough that they can be distributed across a wide area. The key to the whole operation is that the flies need to wake up from their cold-induced dormancy. The warmth of the tropical air does this naturally. As the flies warm up during their descent, their metabolisms restart, and by the time they reach the forest canopy or the ground, they're fully active and able to fly on their own. They then scatter in different directions, dispersing across the territory and beginning their very brief adult lives. Now that we've seen how the flies are bred and distributed, it's time to take a closer look at the insects themselves and understand exactly why this entire elaborate program exists in the first place. The scientific name for these creatures is Cochleomya hominivirax, which translates roughly to man-eating spiral fly, a name that gives you a pretty clear indication of their nature. These insects have large red eyes and metallic blue-green bodies that shimmer in the light. At first glance, they might look like many other blowflies you've encountered, the kind that appear around garbage bins or dead animals. But the critical difference lies in their reproductive behavior and feeding habits. After mating, female screwworm flies seek out warm-blooded animals, and they're looking for one thing specifically: open wounds. Any break in the skin will do. It could be a cut, a scratch, a surgical incision, or any other injury that exposes the flesh beneath. The female fly lands near the wound and lays her eggs there, typically depositing them right at the edge of the damaged tissue. When these eggs hatch, which happens quite quickly, the emerging larvae immediately begin feeding on the surrounding flesh. And here's the truly horrifying part: they don't eat dead tissue. They consume living flesh, burrowing deeper into the wound as they feed and grow. The larvae have specialized mouthparts that allow them to rasp away at muscle tissue, and they produce enzymes that help break down the flesh they're consuming. As they feed, the wound grows larger and deeper, creating a spiral pattern that gives the flies their common name. For the infected animal, this process is extraordinarily painful. The larvae essentially eat the creature alive, and the wounds they create become larger and more severe as the infestation progresses. Once the larvae have fed sufficiently and completed their development, they drop out of the wound, fall to the ground, and pupate in the soil. A new generation of adult flies then emerges, ready to mate and continue the cycle. For centuries, these flies were an absolute nightmare for anyone raising livestock in the southern United States, Mexico, Central America, and the Caribbean. The insects had an uncanny ability to find their way into animals through the smallest openings. Newborn calves were particularly vulnerable because the flies would lay eggs in their navels before the umbilical cord had properly healed. A simple scratch from barbed wire could become an entry point. Even a tick bite, tiny as it is, could provide enough of an opening for a female fly to deposit her eggs. The flies weren't particularly selective about their hosts either. They would infest cattle, which was bad enough given the economic importance of beef and dairy farming, but they also attacked sheep, goats, pigs, horses, and virtually any other domestic animal. Wild animals suffered as well. Deer populations were affected. Squirrels, rabbits, and other wildlife could become hosts. Even pets, dogs, and cats that lived on farms or ranches were at risk if they suffered any kind of injury, and occasionally these flies would infest humans. People who had wounds, surgical incisions, or any other breaks in their skin could potentially become hosts for screwworm larvae. While human cases were relatively rare compared to livestock infestations, they did occur, and they were just as horrific as you might imagine. The pain was intense, the wounds were devastating, and treatment required physically removing all the larvae, which often numbered in the hundreds or even thousands in severe cases. The economic impact of these flies was staggering. Each year, in the southern United States alone, screwworm flies caused millions of dollars in losses to the livestock industry. Animals would die from their infestations, either from the direct damage caused by the feeding larvae or from secondary infections that set in through the massive open wounds. Even animals that survived often suffered permanent damage and reduced productivity. A dairy cow with a screwworm infestation would produce less milk. Beef cattle would lose weight rather than gaining it. The entire agricultural economy of the region was affected by these parasites. The geographic range of these flies was extensive. They were found throughout the Caribbean islands and across Central America. In the United States, their territory stretched from Florida all the way across the southern states to California. Essentially, anywhere that remained warm enough for most of the year could support populations of screwworm flies. The insects couldn't survive extended periods of freezing temperatures, which is why they weren't found in the northern states. But in the south and throughout Latin America, they were simply a fact of life. The flies required only two things to thrive: warmth and access to warm-blooded animals. Given that livestock farming was a major industry throughout their range, and given that wild animals were abundant as well, the flies had essentially unlimited opportunities to reproduce. Each female could lay hundreds of eggs in her lifetime, and those eggs would hatch into larvae that would eventually become adults, and the cycle would continue endlessly. For farmers and ranchers, the situation seemed hopeless. They tried various methods to protect their animals. They would inspect their herds daily, looking for signs of infestation. When they found an infected animal, they would attempt to treat it, cleaning out the wound and removing as many larvae as possible, then applying medications to try to prevent further infestation. But despite all these efforts, the flies always came back. You couldn't spray pesticides everywhere, you couldn't keep all your animals sealed indoors, and you certainly couldn't eliminate every possible way that an animal might suffer a minor injury that could become an entry point for fly eggs. The flies were simply too numerous, too widespread, and too adaptable to be controlled through conventional means. For thousands of years, humans had coexisted with these parasites, accepting the losses as unavoidable. The idea that these flies could actually be eliminated, not just controlled, but actually eradicated from entire regions, seemed like an impossible dream. The breakthrough that would eventually lead to the eradication of screwworm flies from North America came from an unlikely source. A scientist who had grown up fighting insect pests on his family's farm in Texas. Edward Knipling was an entomologist working for the United States Department of Agriculture, and his childhood experiences dealing with agricultural pests had given him a personal stake in finding solutions to these problems. But the idea that would make him famous didn't come from traditional pest control thinking. Instead, it came from understanding the reproductive biology of the flies themselves. Knipling and his team had been studying screwworm flies extensively in laboratory settings, and they made a crucial observation. Female screwworm flies mate only once in their entire lifetime. This is quite different from many other insect species where females might mate multiple times. For screwworm flies, that single mating event determines their entire reproductive potential. If a female mates with a fertile male, she can lay hundreds of viable eggs. But if she mates with a sterile male, she'll lay eggs that will never hatch, and she'll never have another opportunity to mate again. Her reproductive potential would be completely wasted. This observation sparked a revolutionary idea. What if you could flood an area with sterile male flies? The sterile males would compete with fertile wild males for mates. Some females would inevitably mate with the sterile males, and those females would then be unable to produce any offspring. If you released enough sterile males, you could dramatically reduce the number of viable eggs being laid in the next generation. Keep doing this consistently, and the population would collapse. The concept was elegant in its simplicity, But turning it into practice required solving a problem that nobody had tackled before. How do you sterilize millions of flies? When Knipling first proposed this approach in the early 1950s, not a single expert knew how to accomplish mass sterilization of insects. The idea seemed theoretically sound, but the practical implementation was completely uncharted territory. The solution came from an unexpected direction. World War II had recently ended, and scientists had gained considerable knowledge about radiation and its effects on living tissue. Knipling and his team knew that high levels of radiation could damage cells and interfere with reproduction. The question was whether this could be applied to insects in a controlled way. They began experimenting with X-ray machines, passing fly larvae and pupae through radiation at various intensities and at different stages of development. The challenge was finding the right balance. The flies needed to receive enough radiation to become completely sterile, unable to produce viable offspring. But they couldn't be so damaged that they would be weak, unhealthy, or unattractive to potential mates in the wild. A sterile male that no female would choose to mate with would be useless for the program. The flies needed to be sterilized but otherwise normal, capable of competing successfully with fertile wild males. Through extensive testing, the scientists eventually found the optimal formula. They determined the precise level of radiation needed and the best stage of development to apply it. The result was flies that were completely sterile, but otherwise healthy and vigorous, fully capable of mating and competing in the wild. With this problem solved, the stage was set for testing the idea in real-world conditions. The first test took place in 1951 on Sanibel Island, a small island off the coast of Florida. Scientists released sterile male flies there and waited to see what would happen. Initially, nothing changed. The wild fly population continued as before. The scientists kept releasing sterile males, but the results were disappointing. It seemed like the idea might not work after all. But then they tried a different location, Curacao Island in the Caribbean, and something remarkable happened. Within just a couple of months, the screwworm fly population on the island completely disappeared. Not reduced, not controlled, but entirely eliminated. The experiment had worked beyond anyone's expectations. This success sparked what would become one of the most ambitious pest control programs ever attempted. With the backing of state and federal officials, the United States Department of Agriculture launched a full-scale campaign in 1957 to eradicate screwworm flies from all territory east of the Mississippi River. The program involved building the facility in Mission, Texas, breeding millions of sterile flies every week, and releasing them across vast areas of the FART, southern states. It was expensive, it was complicated, and many people doubted it would work on such a large scale. But it did work. By 1959, just 2 years after the campaign began, screwworm flies had been completely eliminated from the entire eastern United States. The success was so dramatic that ranchers in Texas, Louisiana, New Mexico, Arizona, and California immediately began demanding similar action for their states. The program expanded westward, and by 1966, the United States government officially declared victory over the screwworm fly across the entire country. However, there was a problem. The flies still existed in Mexico, and they could easily migrate north across the border. Creating a barrier of sterile flies along the entire United States-Mexico border proved impractical. The border stretches for roughly 2,000 miles, and maintaining an effective barrier of sterile flies along that entire distance would have been enormously expensive and logistically complex. The barrier kept failing, and flies kept re-invading areas that had previously been cleared. The solution was to push the barrier further south. If the flies could be eliminated from Mexico as well, the barrier could be placed further away from United States territory. The program expanded into Mexico, and gradually, the sterile fly barrier was moved southward as more and more territory was cleared. But even Mexico wasn't enough. The flies continued to exist in Central America, and they could still migrate northward. In 1985, scientists proposed placing the barrier at the Isthmus of Panama, the narrowest point of the Central American landmass. This location offered several advantages. First, it was narrow, which meant the barrier could be maintained with relatively fewer resources compared to the alternatives. Second, it connected North and South America, making it a natural choke point. If you could maintain a barrier there, You could protect all of North and Central America from reinvasion by flies from South America. The choice of Panama as the barrier location was fundamentally about economics. Maintaining the barrier there costs approximately $15 million per year, which sounds like a substantial sum. But, according to agricultural economists, the program saves approximately $796 million annually by preventing screwworm fly damage to livestock throughout North and Central America. That's a return of more than $50 saved for every dollar spent, making it one of the most cost-effective pest control programs in history. The barrier has now been maintained continuously for nearly 40 years. Every week, those 14.7 million sterilized male flies are released across the forests of Panama. The factory operates around the clock, breeding the next batch of flies, and crucially, teams of inspectors traverse thousands of square miles on motorcycles, boats, and horses, searching for any sign of screwworm fly larvae north of the barrier. They're looking for random cases, any indication that a fertile fly might have made it through, because even a single mistake, even one pregnant female fly crossing the barrier, could potentially undo decades of work. The program's success depends entirely on vigilance. The people involved take their jobs extremely seriously because they understand what's at stake. If the barrier fails, if fertile flies establish populations north of Panama, the entire region could be reinfested within a matter of years. All the effort, all the expense, all the success of the past 70 years could be undone. This nearly happened in 2016 when screwworm flies mysteriously appeared in the Florida Keys. Deer on the islands began showing signs of infestation, with terrible wounds appearing on their heads and bodies. Nobody knew how the flies had gotten there. The Keys are separated from the mainland, and the barrier in Panama should have prevented any flies from migrating that far north. Yet somehow, fertile flies had reached Florida. The response was immediate and aggressive. Sterile flies were rushed to the Keys and released in massive numbers. Infected animals were treated. Inspectors searched intensively for any sign of larvae. The outbreak was contained before it could spread, and the fly population was eliminated once again. But to this day, nobody knows for certain how those flies reached Florida in the first place. It remains a mystery, and a reminder that the program can never become complacent. Some people might wonder why the program doesn't simply eliminate screwworm flies from South America entirely, solving the problem once and for all. The answer is purely practical. South America is an enormous continent, and screwworm flies exist throughout virtually all of it. You would need multiple factories producing sterile flies, hundreds of aircraft making regular releases, thousands of personnel, and cooperation from every single country on the continent. The logistical challenges would be immense, and the cost would be astronomical. More importantly, getting every South American nation to cooperate on such a program would be extraordinarily difficult. Some countries have explored the possibility. Uruguay, for instance, has looked into implementing a similar program. But the fundamental problem remains: you can't do this in just one country. If Uruguay eliminated screwworm flies within its borders, but Argentina and Brazil didn't, flies from those neighboring countries would simply migrate into Uruguay, and all the effort would be wasted. The program only works if entire regions participate together, maintaining a united front against reinvasion. This is why the United States got lucky with its geography. By pushing the barrier all the way to Panama, American authorities created a situation where one relatively small barrier could protect an entire vast region. It's a unique circumstance that can't easily be replicated elsewhere in the world. Other regions suffer from screwworm flies as well, including different species in Africa, the Middle East, and Southeast Asia, but creating similar programs there would face enormous obstacles. The Screwworm Eradication Program stands as one of the most successful examples of applied scientific innovation in agricultural history. It transformed the lives of millions of animals and saved the livestock industry billions of dollars over the decades. And it continues working today, quietly and efficiently, maintained by those weekly flights over Panama and the dedication of the people who understand that their work matters enormously, even if most of the world has never heard of what they do.